My name is Kathryn Mohror. I'm a computer scientist at Lawrence Livermore National Laboratory, and today I'm going to tell you about a file system we're developing to support scientific applications on high-performance computing systems. Our file system is called UnifyFS, and our effort is supported by the United States Exascale Computing Project. It's joint work between Lawrence Livermore National Lab, Oak Ridge National Lab, and NCSA. And down here at the bottom of the slide, I want to give a big shout out to all the members of the UnifyFS team who are working on developing this file system. UnifyFS is a file system for burst buffers on HPC systems. And our goal is to make using burst buffers just as easy as if you were using a parallel file system, but orders of magnitude faster. To let you know what we mean by easy, we have a code snippet here on the slide. On the left-hand side, we're showing the main function of a program that has a single time step loop that iterates through the time steps. In each iteration, the application does some simulation work, and then it takes a checkpoint. On the right-hand side, we see the implementation of the checkpointing routine. The application specifies the name of a file to write, opens that file, writes some data to it, and then closes it. So to use UnifyFS, all you have to do is change the path that you're using for your file operations. In this example, we've commented out a line, the original line, that uses /PFS, which is meant to represent the parallel file system. And then to use UnifyFS, you just simply swap that out for /UnifyFS. And now all your data goes to our file system. In addition to being easy, UnifyFS is also fast. Here we have some performance results showing how UnifyFS scales for write operations on Summit. And Summit is the flagship supercomputer at Oak Ridge. So on the x-axis, we're increasing the number of processes all writing to a single shared file to UnifyFS. And on the y-axis, we're showing the aggregate write bandwidth over all of those processes. The different color bars represent different ways of running UnifyFS. Here, when we say RAM, we mean that file data is stored in main memory. And this is the default for UnifyFS because it's fast. When we say SSD, here we refer to writing data to main memory until we reach a user-specified limit, after which we spill over to burst buffer. And on this system, the burst buffer we're referring to as SSD. And then we're showing the difference between individual write operations versus batched write operations using list.io commands. So what you see here, the takeaway message, is that UnifyFS is able to scale very well as we increase the number of processes in the job. You might be asking yourself, well, why do we need another file system? Isn't the parallel file system good enough? Well, yes, parallel file systems are awesome. They're very reliable, they scale pretty darn well, and they've served us for many years. However, I think we've all experienced I/O slowdown that can occur when using the parallel file system. That comes from the classic problem of contention. And there are many places in an HPC system where contention can occur that affects I/O. The first place is on the network where your job is running. So this could come from competing jobs also doing I/O at the same time, or even MPI communication from other jobs. There's contention for the I/O resources, the I/O nodes that handle the I/O requests that come from your job and other jobs. And then finally, there's contention for the parallel file system resources itself, from your job, from other jobs running on the same cluster that you're running on, and as a bonus, contention from jobs that are running on other clusters in your compute center, because we share parallel file systems across different systems for convenience. So all of these sources of contention mean that your application could experience significant slowdowns. And we do see that these I/O operations could take on the order of tens of minutes during which an application is not making any forward progress. Another reason that parallel file systems can be slow is that they support what is called general purpose file system semantics. And what that means is that the parallel file system protects your data from any kind of I/O operation that it could occur. So for example, if you have a large parallel job, you could have multiple processes accessing the same byte in a file at the same time, and the parallel file system would protect you from that. And that's great because no one wants corrupted data. However, this kind of protection is not always necessary for HPC applications, and it comes at a cost. If you think about it, in order for the parallel file system to protect your data, every time a process writes to it, it needs to lock that region of the file so that it can't be written to by another process at the same time. So this incurs overhead. To mitigate the I/O problems on HPC systems, system designers have introduced new levels of storage into supercomputers, and we refer to these as burst buffers. And all they are storage devices that are put into the system closer to compute nodes than the parallel file system. They serve as a cache between the compute nodes and the parallel file system for I/O operations. We see two models of burst buffers today. The first is called a local burst buffer model, and here the storage devices are located on the compute nodes themselves. We see this model in systems like Sierra at Lawrence Livermore and Summit at Oak Ridge. The other model is called a shared burst buffer model, and here storage devices are external to the compute nodes and they are shared by a group of nodes. And these could be dynamically allocated to a group of compute nodes or possibly statically allocated. We see the shared burst buffer model on Create data warp systems in particular, like Cori at NERSC or Trinity at Los Alamos. Both of these models have their pros and cons. We'll go through the good side first. For local burst buffers, these are fast. They are attached to the compute nodes. There's no network involved, and there's no contention. You are not sharing these devices with any other jobs on the system. And there's also a potential for very excellent scaling performance. As you add compute nodes to your job, as you scale up, you're automatically adding storage resources that your job can use. So it scales very well. For the shared burst buffer model, if you think about it, a shared burst buffer is kind of like a mini parallel file system. So it's a single shared mount point. And that means it's really easy for applications that use shared files or for producer-consumer applications. And by producer-consumer, I mean coupled applications that communicate through data files. And so the classic example of this is a climate model, like where maybe you have an ocean component that outputs a file that is read in by the atmosphere component. Okay, so now for the cons, the bad side. For local burst buffers, these are really challenging to use if you have an application that is writing shared files or a producer-consumer application. And the reason is that these storage devices are local to a compute node. And so any data that's written on node 0 by reg 0 is not visible over on node 4. And the same is true for producer-consumer applications. The files that are output are not visible across the compute nodes. For the shared burst buffer model, it's not quite as fast as the local burst buffer model. So, it's a shared resource. There could be contention issues. It's also not node local, so there can be network issues. The model that we target for UnifyFS is the local burst buffer model, and we are specifically targeting the problems with it in that it is very challenging to use for shared files and by producer-consumer applications. Here are some performance results to motivate the use of node local burst buffers. So we have scaling results for two different supercomputers. These are both Livermore systems. One is Atlas and the other is Lassen. And in each graph, we are comparing I/O operations to node local storage or burst buffers, and that's the blue and green lines. And we're comparing that with the performance of the parallel file system, which is the orange-brown line. And probably what you see immediately is that the parallel file system on both systems does pretty well at first and is comparable to the performance of node local storage. However, as you scale up, at a certain point, you saturate the available bandwidth of the parallel file system, and you're just not going to be able to get any better than that because it's saturated. On the other hand, if you look at the node local storage I/O operations, they scale as you add compute nodes in the job and perform very well. So on Atlas, we measured them performing as much as 1,000 times faster than the parallel file system, and on Lassen as much as 300 times faster. And I want to point out, these measurements were not taken with UnifyFS. They were taken with a sister project of UnifyFS called SCR, which stands for the Scalable Checkpoint Restart Library. And many of us who work on UnifyFS at Livermore also work on SCR. And actually, SCR was a problem we had with SCR was an inspiration for the development of UnifyFS. SCR supports, SCR improves checkpointing operations of applications by using node local storage to cache checkpoints. And this is a perfect arrangement for applications that write per process file. So every MPI process writes its own file. It goes to node local storage. It works really well. However, as we said before, shared file operations are not supported. And so we wanted to be able to support a wider class of applications with SCR. And so we embarked on the development of UnifyFS so we could couple it with SCR and support more applications. So in order to make using node local burst buffers easy for shared files, what we do with UnifyFS is create a shared namespace across the distributed burst buffer in a user's job and give it a name, /UnifyFS. And so now you can use this mount point just like you would use any other mount point to a file system in your regular I/O. You can use this directly by your application, or if you're using higher level I/O libraries like HDF5 or MPIAO, you can use those as well. We have designed UnifyFS to be fast for HPC applications. So we have tailored UnifyFS to optimize for the way that HPC applications behave. So if you remember a while back, I talked about one of the problems with the parallel file system is that it supports general purpose file system semantics. So in UnifyFS, we're taking a bold move and we are backing away from that. And this means that we can get faster I/O for your application. The other reason that UnifyFS is fast is because it only exists for your job. You are not sharing a UnifyFS instance with any other jobs on the system. So there's no contention when you're trying to do your I/O. Here's a high-level overview of how UnifyFS can work with a user's job. So the first point I want to make is that UnifyFS is completely in user space. So this means, first of all, you don't have to ask for any sysadmin help to get this installed for your job. You can download and try it out all on your own. And the second point is that by implementing it in user level, it's faster. There is no overhead of traversing in and out of the kernel for I/O operations. So at the top of this diagram, you see how a user can insert commands into their regular batch job to get UnifyFS started, run their application, and then terminate UnifyFS. And so you take your modified batch file and you submit it to the resource manager just like you normally would. And then when your allocation is granted and the commands in your batch script are executed, UnifyFS is spun up for your job across all the compute nodes. And now you have the UnifyFS mount point available to your job, and it can support, whatever application IO, or excuse me, whatever IO your application is doing. So this could be shared file checkpointing, file per process checkpointing, or maybe you're using some high-level IO library like MPI-IO, or a checkpointing library like SCR. And so UnifyFS intercepts all the IO operations from your application at the user level and handles the IO appropriately. For optimizations, for example, we always write data to node local storage, RAM disk first, and then fall back to SSD. And the reason we do this is because it's fast. So I said that we optimize UnifyFS based on typical HPC IO behavior. And I'm going to use the next few slides to talk about what those typical behaviors are and how we optimize for them. On the left-hand side, we have a skeleton of a typical HPC application, sets up MPI, reads its input so it can get going, and then has a time step loop. In each time step, the application does some simulation work, communication and synchronization, and then writes some output. This could be visualization files or a checkpoint or whatever. On the right-hand side, the circles here represent compute nodes, and the little squares in the circles represent data from the processes on those compute nodes, and then the cylinders at the bottom are the parallel file system. So the first thing we notice from this example is that in HPC applications, reads and writes occur in distinct phases. So at the beginning of the execution, the application was reading, and then periodically during the application is writing. So the reads and writes are not interleaved. It's just one or the other. The second thing that is typical of HPC applications is that the reads and writes are performed to regular offsets in the file. And so you can see that the data from the processes in our example have been chunked into different regions in the file. And the actual output from a real HPC application might not be as regular as this, but the IO patterns are regular and computable. And in contrast to something like a database IO workload where the reads and writes could be randomly distributed throughout the file. The last behavior that is typical of HPC applications, and this is particularly true with checkpoint restart workloads, is that when an application does read during execution, it's most likely going to need the data that it wrote. So if you think about it, if you have your MPI application executing and it's periodically writing checkpoints, when it crashes and restarts, rank 0 is going to need the data that rank 0 wrote in order to restart. So yeah, these behaviors are pretty typical of all kinds of common HPC workloads that you can think of, like checkpoint restart, reading of input decks when an application first starts, periodic output like visualization or other output dumps, or producer-consumer workloads like the climate model that we talked about earlier. Okay, so now that we understand how HPC applications behave with respect to I/O, we can understand UnifyFS's model for optimizing on that behavior. We call our semantics that we employ lamination semantics. And if you're not familiar with the process of lamination, I have an illustration here at the bottom of the slide. To laminate a document, so this could be an important document like your wedding invitation or maybe your diploma, you take that document and you put it inside of a plastic sleeve. And then you take that plastic sleeve and you feed it into a machine. And the machine melts the edges of the plastic such that now your document is protected. It's encased in plastic, and so you can spill coffee on it and it'll be fine, but you also cannot modify it. So it's protected now. So we base our UnifyFS optimizations on this idea. Before lamination, files can be modified. So processes can write to them willy-nilly. The caveat there is that file data may not be visible to all processes before lamination. So, rank 4 may not be able to see rank 0's data, especially if they're on different nodes. When the HPC application is done with the file, it initiates a lamination operation. And when this happens, UnifyFS renders your file read-only, so it protects it, encases it in plastic, so to speak, and also synchronizes all the data across your job. So now, any process on any node can read the final state of the file, and you can also transfer the file data to external storage. So the key reason we are making these optimizations is for performance. So here we have some performance results showing using UnifyFS with different configurations on when you can read the data before lamination. On the x-axis, we have increasing node count, and on the y-axis, bandwidth and log scale. And the different color bars represent different ways you can read data in UnifyFS. So the darkest color represents being able to read data from any location before lamination. The middle green bar represents being able to read data from any process written on the same compute node that you're running on. And the final green bar represents the case where a process only ever reads the data that it wrote. And so you can see that the third case, which we said was common for HPC applications, especially for checkpoint restart, results in the best performance. So this is why we are making these assumptions in UnifyFS. Okay, now that I've given you an overview of what UnifyFS is, I'm going to walk through a brief tutorial on how to use it. We'll talk about how you can get and build UnifyFS, how to alter your application and link it with UnifyFS, get your environment set up, and run your application and get your data from UnifyFS. To build UnifyFS, by far the easiest thing to do is to use SPAC. And if you're not familiar with SPAC, it's a package manager for HPC that really takes a lot of the pain out of building a particular tool and all its dependencies on an HPC platform. So I really recommend you get it to help build UnifyFS. If you have SPAC, building UnifyFS is as simple as SPAC install UnifyFS. And SPAC will go out and grab UnifyFS code, all the dependencies, pull them down for you, and build them. So it really makes life easy. And then you can execute SPAC load UnifyFS, which will populate your environment so that you can use UnifyFS with your application. We also support building the conventional way, configure, make, install. That does mean that you have to manage the dependencies yourself. We do have extensive documentation on how to do SPAC builds as well as other builds of UnifyFS. So once you have UnifyFS built and you're ready to use it, you need to understand how to modify your application. So here we have an MPI application, just a skeleton of one, right? And in the middle there, it's doing I/O operations, opening a data set to Lustre and writing hello world. To use UnifyFS in this example, all one needs to do is change the path from /cluster to /UnifyFS, and you're good to go. If you're not using MPI, if you have a serial application, you have to do a couple more steps in your code. So here we've inserted calls to UnifyFS mount, which takes as an argument the name of the mount point you want to use in your code for UnifyFS, and UnifyFS unmount. So when you're using an MPI application, we hide that step from you, but we don't yet have it hidden for serial applications. UnifyFS works by intercepting the I/O calls that are made by your application or by I/O libraries that you're using. And so in order for this to work, you need to link your application with the UnifyFS library. We support static linking. This is a much more complicated process, so it's not the recommended way. If you're interested in static linking, I encourage you to check out the documentation. Dynamic linking is definitely the recommended method for using UnifyFS. We use what's called the gotcha library for dynamic interception. So this is a very robust way of doing dynamic interception. And so then when you're building your application, you simply link with the UnifyFS gotcha library, and it will intercept all your I/O operations. There are quite a few configuration options to UnifyFS. So for example, at the beginning of the talk, I said that the default location that UnifyFS stores file data is in main memory. However, main memory is a limited resource, so you may want to set bounds on how much memory UnifyFS can use. So that's an example of a configuration setting that you can set. We have these settings that are available documented in our user's guide. UnifyFS.readthedocs.io. You can look in there. You can set it using a configuration file, environment variables, or options to our startup utility. Okay, so now that you have everything all set up, how are you going to run your code with UnifyFS? To illustrate this, I'm going to show you how to do it in a bash script. So in this example, we've allocated 8 compute nodes, showing those at the bottom there. And then what we do is we add lines to your batch script to start up the UnifyFS file system. So the command is UnifyFS start, and the first argument here, called shared is a bootstrapping argument, and that points to a place on the parallel file system. And you also give it the mount point that you want to use in your job, so /UnifyFS in this case. And when this executes, it will launch a UnifyFS daemon on all of the compute nodes in your job. And those compute nodes will work together to set up the shared namespace for your application to use, /UnifyFS. Once UnifyFS is up and running, you launch your job just like you normally would. And so it gets launched onto the compute node. And then because it's linked with the UnifyFS library and is doing I/O operations to /UnifyFS, all the I/O is routed through the UnifyFS library into the UnifyFS file system. Then when your job is over, you simply execute UnifyFS terminate, and the UnifyFS daemons will tear down the file system and exit. An alternative method to getting UnifyFS running in your allocation is to use integration with resource managers. Currently, we have support for LSF, which is the resource manager on Summit. And this is the only piece of UnifyFS that requires administrator support. So the scripts end up running as part of the resource manager, which is a privileged operation. So you need help with that. So if you do have this installed at your center, then instead of executing the UnifyFS start command, as I showed on the last slide, here you simply add some flags to your launcher command to the resource manager. So alloc flags UnifyFS. And we don't currently have support for Slurm, but this is in progress. So a really key point is, how do I get my data into and out of UnifyFS? So there's 3 ways you can do this. The first is we have a UnifyFS transfer program. The second is that we provide an API that you can use from within your application. And the third way is options to the UnifyFS start command. The easiest way probably to move data into and out of UnifyFS is to use the executable transfer program. So here it's just as easy as it sounds. It's the transfer executable, source, and destination. And the key points here are that the source or the destination need to exist in UnifyFS, and the other location needs to be outside of UnifyFS. And you do need to make sure that your files are laminated. If your files are not laminated before you transfer them, you may not get the correct data. And since getting the correct data is important and the whole reason you ran your simulation, please remember to laminate. So here's an example of how you might use the transfer executable. So this is a batch script that we've seen before in the example. After we run our hello program, we run transfer executable and take file 1 and move it out to the parallel file system. Here's method 2, illustrating how to use the transfer API from within your application. And you might do this if you need finer control over what files end up on the parallel file system and when. So in this example program, we're writing a file and then we're going to transfer it out. So the first thing that is important is that we need to make sure to laminate the file before we transfer it. And currently, right this moment, laminate is implemented by executing chmod. We do have plans in the future to extend how this happens. For example, applications could choose to always laminate files on close. Whenever you close a file, it will be laminated. But that doesn't work for every application. Some applications close files and then want to modify them. So in that case, we plan to provide an explicit laminate call. So UnifyFS laminate when you want to take care of your file, or possibly on unmount, you just laminate everything in the UnifyFS file system. And we do plan to make this configurable at runtime, so you can choose which lamination operation you would like to use. So once your file is laminated, you can call the UnifyFS transfer API with your source and destination file to move data in or out of UnifyFS. The last method to move data in and out of UnifyFS is to use options to the command line tool. Here the options are stage in and stage out. Stage in brings data in to UnifyFS, out takes it out. And in each case, the argument to the option is the name of a file. And inside that file, so inputs in this example, would be a listing of the files that you want to bring into UnifyFS. And in the same way, outputs would be a file containing a listing of the files that you would like to move out of UnifyFS at the end of the job. So here's one more example of how to use UnifyFS with an application. In this case, we're illustrating how you would do it with a higher level I/O library, HDF5 here. So we have a toy code, familiar from the other examples, where we're showing the main function on the left-hand side with the main time step loop, and on the right-hand side, the checkpointing routine that opens a file and writes data to it and then closes it. So as before, to use UnifyFS, all you really need to do is change the path to point to the mount point / UnifyFS, and all your I/O will be routed to our file system, even if it's going through HDF5. And also in this example, I have added a step to laminate the file. So now that you already understand about laminating, I will point that out. So it's really quite easy to use UnifyFS even if you're using a higher level I/O library. I glossed over a whole lot of details in this talk. So if you want to learn more, I encourage you to check out our documentation, unifyfs.readthedocs.io. If you do that, please go down to the bottom where that arrow is pointing on the screen and choose version latest. So we're a relatively young project. We've been together almost 4 years now, which is pretty young for a file system. And we are constantly adding improvements, etc. So, if you look at the latest version of the docs, you will be sure to get the latest updates on what we're doing. If you want more examples on how to use UnifyFS, we have plenty of examples in our examples directory. So to conclude, our goal is to make using burst buffers super easy, portable, and fast. We need early users. So if you're interested in this, please check it out. Please contact us and let us know what features are important to you. Maybe we have missed something key about your application that would be really cool to support in UnifyFS. Please let us know. We're on GitHub. And again, there's another link to our documentation. And you can always email us at unifyfs@exascaleproject.org.